confusing, but that's the way the chemists do it. Okay, let's talk about pH. pH is an interesting concept. It's something that the general public is familiar with. In fact, there's some shampoo commercials where people talk about pH balanced shampoo. So it's in the general knowledge. Water dissociates, that is, it spontaneously breaks apart into a proton, which we symbolize as H+, and a hydroxide ion, and it's an equilibrium. Now, anytime you have an equilibrium, you can write the equilibrium as products divided by reactants. So in this case, the products are a proton and a hydroxide ion, and the reactant is water. And it's equal to a constant, the equilibrium constant. Now, and we use these square brackets to indicate concentration expressed in molarity. Now, water, distilled water, has a concentration of 55.55555 gram moles per liter, and so distilled water, the concentration of water in a beaker of water is constant, so we can bring that constant water concentration over to the other side, and so that product of Kc times 55.5555 is K sub W, W standing for water. And just by an accident of nature, which is really quite wonderful, if you multiply the proton concentration times the hydroxide concentration, you always get this constant 10 to the minus 14. That is, K sub W has the numerical value of 10 to the minus 14. So no matter what you do, always the product of the proton concentration times the hydroxide concentration equals 10 to the minus 14. Well, it's inconvenient to deal with such small numbers, so chemists have developed a system using log base 10, where you take the inverse of the proton concentration, give the log of that, and they simply call that the pH. If you take the inverse of the hydroxide ion concentration, log base 10, that's called the pOH. So based on this relationship, which is given by really thermodynamics, the pH plus the pOH always has to be equal to 14. Once you define these and you've made this measurement right here, then this must be true. Now, in terms of nomenclature, if we have a case where there are more hydroxide ions than protons, the pH will be greater than 7, and we call that an alkaline solution. If we have a case where there are more protons than hydroxide ions, the pH will be less than 7, and we call that an acidic solution. So let's do a simple problem with this. We've got a 10 gram per liter solution of sodium hydroxide, and what's the pH of this? And noting that sodium hydroxide completely dissociates into sodium ions and hydroxide ions. So the first thing we have to do is calculate the molecular weight of sodium hydroxide. There's 1 sodium, 1 oxygen, 1 hydrogen, so the molecular weight is essentially 40. So if we have 10 grams and 40 grams per gram mole, that 10 gram per liter solution is a 0.25 gram mole per liter solution. We could also say that's 0.25 molar. Then we look at the hydroxide concentration. We said that it completely dissociates, so that means for every gram mole of sodium hydroxide, there's 1 gram mole of hydroxide ion. So the hydroxide ion concentration is also 0.25 gram moles per liter, or you could say it's 0.25 molar. Now the pH, based on the definition, is log base 10, 1 over the concentration, so that becomes 0.602, and then based on this relationship right here, the pH would be 13.4 essentially. So that's very strongly alkaline. The pH is way above 7, so you can go above 14, but this is a very strongly alkaline solution. Okay, we're going to shift gears now and talk about chemical reactions. What happens in a chemical reaction is the elements or molecules rearrange themselves to form more stable, that is, lower energy molecules. The reaction is highly favored if electrons are transferred from an element that loosely binds its outer electrons, that is, with low electronegativity, to one that tightly binds them, that is, with a high electronegativity. The element or compound that donates the electron is called a reducing agent, and the element or compound that receives the electron is called the oxidizing agent. And I've got to say that this is perhaps one of the most complicated or confusing aspects of chemistry. These words get very, very confused. So let me do my best to explain this to you. Let's say, for example, I have elemental potassium, and I contact it with elemental fluorine. Recall from our earlier discussion, if I can find it. Here we go. This is the electronegativity chart. Recall that fluorine is very, very highly electronegative. It has an electronegativity of 4. And what we're going to do is react it with potassium, which is right here. It has 0.8. So this is 0.8, and fluorine is 4.0. There is a very, very large difference in these electronegativities. So this is an ionic reaction. The electrons in the potassium are stripped away and added to the fluorine, which takes on a negative charge, and the potassium stays behind as positive. And then what we can do is take a look at sodium. Sodium is here on the periodic table. It has 0.9 as its electronegativity. Again, the fluorine is 4.0, a big difference, and it's an ionic reaction. And then here we have lithium, which has a 1.0 on the electronegativity scale. Again, fluorine is 4.0, and again, we have yet another ionic reaction. Now, my point is that the bigger the difference between the electronegativity, the more highly favored the reaction. You can think of this as being a very energetic reaction, that fluorine really wants that electron. It takes it away from the potassium, and an awful lot of energy is released in the process. Now, in this case with lithium, lithium is a little bit better at hanging on to its electron, so when fluorine takes it away, it wasn't quite as favored as the potassium reaction. Now, to add confusion, we would say that fluorine is reduced and the alkali metal is oxidized. Now, this is what's crazy about it. Take a look at this. We're saying here fluorine is reduced and potassium is oxidized, but we say potassium is the reducing agent and fluorine is the oxidizing agent. So it sort of swirls around your head, and what are you talking about? Well, think of it this way. Fluorine causes the potassium to be oxidized, and potassium causes fluorine to become reduced. So the nomenclature here is based on, let's say I've got a jar filled with potassium. As I add fluorine into that jar, fluorine is oxidizing the potassium. And so we would say that the fluorine is the oxidizing agent that caused the fluorine to become oxidized. Now there's a little mnemonic device that can help you here. It's called oil rig. What we're doing now is we're talking about loss or gain of electrons. To be oxidized is to lose electrons. To be reduced is to gain electrons. So what's happening here is the fluorine is taking electrons from the potassium, so it is becoming reduced, right? Reduced is to gain electrons. Conversely, the potassium just lost its electrons, so it became oxidized. Oxidized is lose electrons. So hopefully that's about as clear as mud, but hopefully a little bit better than what you had before coming into this class. Now, this reaction that I've just shown here, which will occur naturally, we can reverse it in an electrochemical cell. So let's say, for example, I have a power source. I'm showing here a battery. I have one electrode called an anode, another electrode called a cathode. I impose a positive charge on the anode and a negative charge on the electrode, on the cathode. What will happen is, because this is a positive charge, all these negative species are going to migrate to it, and what's going to happen is the electron that's on this fluoride ion is going to be stripped off at the anode and pumped up using the battery and pushed on to the cathode. So this is the reaction that occurs at the anode. Again, the negative fluorines are attracted to the anode. The electrons are stripped off and pumped over to the other side. Once those electrons are stripped off, we have gaseous fluorine literally bubbling from the surface. And then we've taken those electrons, we're pumping them onto the other side. This plate is negative in charge. The positive potassiums are attracted to it. They pick up those electrons, so we take the positive potassium plus the electrons, and we end up with elemental potassium. And what you would see visually is this cathode being coated with a metal of elemental potassium. Now this is used commercially. For example, let's say you had some jewelry and you wanted to gold plate it. What you would do is form a solution of gold salts, maybe gold chloride, for example, and take your jewelry and attach a wire to it. So let's say that this is a ring. We would attach the wire to the ring, dip it into our solution of gold salts, and we apply a voltage. What will happen is the chlorine will migrate over to the anode and bubble off as chlorine gas, and the electrons that are pumped over here will take the positively charged gold and plate it onto the surface. So you can get very, very thin coatings of gold onto metal using this electroplating process. This is also commonly done in the semiconductor industry. A lot of the contacts in the cards that you put in your computer are gold plated so there's no corrosion, and so they plated the gold using an electrochemical cell like this. Again, some definitions. The cation is the species that's attracted to the cathode, and the anion is the species attracted to the anode. And what's confusing about this is the cathode is negative, but the cations are positive. And conversely, the anode is positive, but the anions are negative. And I apologize for it being so confusing, but that is the way that people describe these things. Now, we've just been talking about ionic reactions. This idea of electronegativity and energy associated with changes in electronegativity can be borne out with covalent bonds as well. Let's take a look at these. We've got three species that we're going to be discussing here. Carbon, which has 2.5 as its electronegativity. Hydrogen, which is 2.1, and oxygen, which is 3.5. And you can, all those numbers came off of this electronegativity chart. Now, let's take a look at the carbon. This carbon is surrounded by 4 hydrogens. The carbon is more electronegative than the hydrogen. So what's going to happen is the electrons are going to spend a little bit more of their time around the central carbon, and these hydrogens are going to have a slight positive charge as a result. If we then introduce an oxygen into the chemistry here, by the way, this is methane. This is called methanol. So by introducing an oxygen into the chemistry, oxygen has a very strong electronegativity. So what's going to happen is the oxygen is going to become the center of charge, and the hydrogen is going to give its electrons to the oxygen. The carbon is going to give some of its electrons to the oxygen, and even these hydrogens are going to give some of their electrons to the oxygen. So the oxygen is the bully; it's taking the electrons. Then what we have here is we've removed some of the hydrogens. This species is called formaldehyde. So the demand that this oxygen has for electrons now has to be borne largely by the carbon. So the carbon is becoming increasingly positive as a result of that. This species now we have two oxygens all demanding electrons. This species is called formic acid, and this poor carbon is losing out because these bully oxygens are taking away their electrons, making it become increasingly positive. It has a little bit of hydrogen around to share the burden, but then finally here we have carbon dioxide. There's nobody to help satisfy this insatiable demand for electrons, and so the carbon is becoming quite positive at this point. So the idea is that in regard to carbon, the carbon over here is reduced, that is, it gained electrons from the hydrogen, and over here the carbon is oxidized because it has lost its electrons. It lost them to the oxygen. So if, for example, I have methane and I react it with oxygen, I get CO2 and water. What's happening is the oxygen is the oxidizing agent and the methane is the reducing agent, and in the process of this reaction the carbon became oxidized, that is, it lost its electrons, and the oxygen became reduced, that is, it gained its electrons. Now, if we were to start with methane and react with oxygen, you can see that there's a big difference. We're going all the way from the left, all the way to the right, so there's a lot of energy that comes out of this reaction. If I were then to react methanol with oxygen, methanol is already partly burned. It's already partly oxidized. So if I burn methanol as a fuel, I don't get as much energy out of it. If I burn formaldehyde, it's partly burned, and this formic acid is almost completely burned. So if I try to combust from formic acid, I don't get very much energy at all. So the idea is big deltas in your redox, or I'm sorry, your electronegativity cause large amounts of energy to be released. Okay, I've just given this example of methane reacting with oxygen to form carbon dioxide and water. Another thing that comes out of this is heat. And so combustion is the process of burning a fuel with oxygen primarily for the purpose of generating heat. And again, the fuel would be called the reducing agent, and the oxygen would be called the oxidizing agent, because the oxygen is causing the fuel to become oxidized. Now, a very, very important topic, and you're almost guaranteed to see a question of this type on the exam, is to balance a chemical reaction. When I was a freshman learning how to balance reactions, I used the by guess and by golly method, where I would just sort of fool around with the coefficients until they eventually balanced. As I got more mature, I found a rational way to balance reactions. What you do is you follow the sequence. First of all, you write the reactants on the left of the arrow and the products on the right of the arrow. Typically, you would base the calculation on one molecule of a reactant or product. The other species are given variables A, B, C, and so forth. Then you write equations for each element in matrix form and solve the matrix for A, B, and C. So here I have an example. This is ethylene, which I'm going to burn. For some unknown reason, it's too expensive to burn, but let's imagine we do. We're going to burn ethylene with oxygen, and I don't know, I'm going to burn 1 mole of ethylene. I don't know how many moles of oxygen, carbon dioxide, or water that I'm going to get from this. So there are 3 elements involved in this reaction: carbon, hydrogen, and oxygen. So I'm going to do, first of all, a carbon balance. So this species has 2 carbons. This species has 0 carbons. This has 1 carbon, 0 carbons. I've got 1 of these 2 carbon species, and I've got B of these 1 carbon species. So I write down the formula: 2 plus 0 equals B plus 0. And very easily we find out that B has to be 2. There's 1 unknown in this equation that can be solved. 1 equation, 1 unknown. Next, let's talk about the hydrogen. There are 1, 2, 3, 4 hydrogens in this species. There's only, of course, 1 of them. There aren't any hydrogens in this species, so we put a 0 down. There aren't any hydrogens in this species, so we put a 0 down. But there are 2 hydrogens in this species, and there are C of them. Again, we have 1 equation, 1 unknown, and we can find out from that that C has to be 2. Finally, let's do an oxygen balance. There isn't any oxygen here, but I have 2 oxygens in this species, and there are A of them. I have 2 oxygens in this species, and there are B of them. And I have 1 oxygen in this species, and there are C of them. Fortunately, I already know B and I already know C, so I can solve and find A. And so the balanced equation is shown here. 1 ethylene plus 3 oxygens goes to 2 carbon dioxides and 2 waters. So that you could have found it just by playing with the numbers, but this is systematic and it will always lead you to the correct answer. Okay, we're going to be talking about yet another topic, which is reaction kinetics. And the idea is we have species A and species B reacting to form product C and product D, and we have A moles of A, B moles of B, forming C moles of species C and D moles of species D. Now we have a number of scenarios here. The first scenario I'm going to talk about is what we call elementary reactions, where the reaction goes exactly as written with no intermediate. So truly, let's say A and B are 1. 1 mole of A slams into 1 mole of B. They stick together and form C. And that truly is exactly what happens at the elementary level. If we have a gas phase reaction, the rate of this reaction, that is how fast does A and B react to form C and D, V rate is given as the rate at which the partial pressure of species A goes away, the rate at which species B goes away, or the rate at which partial pressure of species C increases, or the rate at which the partial pressure of species D increases. And there's a single rate, so we normalize all of these by dividing by the respective coefficients. So regardless of what species you're going to follow, provided you normalize them with the stoichiometric coefficients, you will always get a single number for V rate. The other thing to be aware of is that we use a negative sign in the case of reactants, and we use a positive sign in the case of products. Now, the rate at which A and B go to the right is given by this expression. It's proportional to the amount of the partial pressure of species A raised to the A power, the partial pressure of species B raised to the B's power. So this is the forward direction. The reverse direction, C and D can react and form A and B, is given by this. It's proportional to the partial pressure of species C raised to the C power, the partial pressure of species D raised to the D power. In this case, the proportionality constant is K prime. So we have a forward rate constant, K, and a reverse rate constant, K prime. And so the net reaction in the forward direction is given by this expression. Now, at equilibrium, what we mean is that the rate is 0. That is, there is no net production of C and D at the expense of A and B. A and B goes to the right, and C and D goes to the left, and it's in some sort of balance. So again, our rate goes to 0. If we take this rate equation and set it equal to 0, we can come up with this expression, which is the ratio of the forward rate constant to the reverse rate constant. And of course, these are both constants, and we call it a new constant, case of P. And notice it's always products over reactants. Now, if we have a situation where Kp is very, very large, what that means is that's an irreversible reaction, meaning it goes all the way to the right, and it's favorable as we wrote it. If we have a situation where Kp is approximately equal to 1, that means that there's a similar amount of products as reactants, and we would call that a reversible reaction. And if Kp is very, very small, that means there's lots of reactant and hardly any product. That also is an irreversible reaction, but we wrote it backwards. It should have been written the other way. Now, in the case of liquid phase reactions, rather than expressing our concentration as a partial pressure of each species, here we express it as a concentration, such as a molarity, for example. And it's the same argument that if the reaction goes to 0, there's a proportionality or an equilibrium constant, which is the ratio of the forward and reverse constants, and you do the same thing with products over reactants, each raised to their respective stoichiometric power, and that just gives it to an equilibrium. So we've talked about gas phase reactions, liquid phase reactions. Solid phase reactions are interesting. Wherever you have a solid, if you have solid products or solid reactants, you just pretend they're not there, because their concentration stays the same. It's just a solid. The concentration of the solid in the solid is a constant, so that just gets buried into our equilibrium constant. Now, so far we've been talking about elementary reactions. Again, they go exactly as written. A and B really do slam together and form C and D. Non-elementary reactions are, sure enough, the overall stoichiometry as A and B goes to C and D, but there's a lot of underlying substructure that you have no idea exactly what's going on, how A and B combine to form C and D. In that case, the rate equation must be determined experimentally. But interestingly, the equilibrium constants are defined the same way as they were with the with the elementary reactions. Now, some other things to be aware of with reactions are that when you increase temperature by about 10 degrees Celsius, the reaction rate typically doubles. And so what that means is that if this is the rate of reaction as a function of temperature, here it is at cold, I increase it by 10 degrees, I double it, I increase it another 10 degrees, I double it again, another 10 degrees, I double it again. What you see is you can have reactions go explosively or exponentially as you increase the temperature. Now, I mentioned catalysis previously. I mentioned in the context of chlorine-free radicals destroying ozone. The general definition of a catalyst is it provides an alternate reaction path that can increase the rate of reaction without actually being consumed in the process. Notice that it does not affect the equilibrium. The equilibrium is not affected by a catalyst. This is a very common question that they like to ask. People tend to get confused between equilibrium and rate. Again, a catalyst will increase the rate, but it does not change the equilibrium. Now, if we have an exothermic reaction, as A and B are converted into C and D, we get heat evolved from that, and in an endothermic reaction, it requires heat in order to convert A and B into C and D. Now, a very famous principle connected with not only reactions but other processes is Le Chatelier's principle. It says when a force is applied to a system at equilibrium, the system establishes a new equilibrium that minimizes the effect of the applied force. If we apply Le Chatelier's principle to chemical equilibria, if we have an exothermic reaction, then it is favored at low temperature. What happens is the reaction wants to get rid of heat because it's generating heat. It's much easier to get rid of heat if you have cooling water there that it can dump it to. So if you want to drive an exothermic reaction, do it at a low temperature. If you want to drive an endothermic reaction, it wants heat. It's easier to put heat in by having a flame or some high temperature steam to dump the heat in there. And so to make an endothermic reaction favored, run it at high temperatures. Another relationship to Le Chatelier's principle is that if you have a reaction where there's an increase in moles, that is, A plus B is smaller than C plus D, that says run the reaction at low pressures. If you have a case where there's a decrease in moles, that is, C and D is less than A and B, then you should run the reaction at a high pressure. So a classic example of this is ammonia. Ammonia is a key chemical that's needed in our society to make fertilizer. The balanced reaction is you take 1 mole of nitrogen, 3 moles of hydrogen, and you get 2 moles of ammonia. You can see here we're starting with 4 moles, 1 plus 3, and ending up with 2 moles. So we're having a decrease in number of moles, which Le Chatelier says run that at high pressure. And truly at industrial reactions, they run these at about 200 to 300 atmospheres of pressure. Enormous pressures, and even then it doesn't go to completion. It only goes to 30 to 40% of completion. Another reaction is you can take ethanol and form ethylene and water. I hope I have that balanced. Here we start with 1 atom and we get 2, and so that would be favored at low pressure according to Le Chatelier's principle. Okay, the last topic we're going to discuss is organic chemistry, and I must say that this would be a very brief discussion because there's actually a whole course devoted to this single topic. Organic chemistry is the study of carbon chemistry. Alkanes are a class of organic chemicals. They have single bonds, and this is the nomenclature of alkanes. As you add carbons, this is how the names change. If we have double bonds, those are called alkenes. And if we have triple bonds, those are called alkynes. If we have an OH group, that's called an alcohol. If we have this group, it's an aldehyde. I can give you some examples. Here is ethanol as an example of an alcohol. Here's formaldehyde, which is an example of an aldehyde. Here we have carboxylic acid, which has that group. Acetic acid or vinegar is an example of that. Esters have this group. Ethyl acetate is an example of that. Ethers are 2 R groups joined by a single oxygen. Dimethyl ether is an example. And ketones have this structure. And again, R can really be anything. I've used methyl groups as examples, acetyl groups, and others. Even hydrogen can be considered R. Okay, with that I'd like to stop for a moment and take a breath, because we've just gone through all the theory associated with this chemistry.